Hello everyone. This video is a continuation of section 5.5 from Math in Our World. In this video we will finish the section and talk about the identity and inverse properties, and then look at a summary of all of the properties of real numbers and identify which properties were used in various expressions. So to begin, let's look at the identity property. We have one for addition and one for multiplication. And this property says that the sum of any real number plus 0 gives you that same real number. So we have this very special number 0, which is called the identity for addition. So if you think of your identity as like who you are, right, then something that doesn't change your identity in terms of numbers is 0. Okay? So, for example, 18 plus 0 is still 18, and that is the identity property. Now I can just replace 18 with any number. Your book calls this A. A plus 0 is still A. And it doesn't have to be, here I've used a natural number, 18, but it could be anything. It could be a fraction. 1/2 plus 0 is still 1/2. I can switch these. I can say that 0 plus square root 4 is still square root of 4. I could do irrationals. Pi plus 0 is still pi. And that's the identity property for addition. Now, we have an identity property for multiplication, but we have a different identity. So, for example, if I did 18 times 0, that's not still 18. So 0 is not the identity for multiplication. 1 is the identity for multiplication. 1 is the thing that you can multiply by any real number without changing its value. Alright, so for example, here's a complicated real number, the square root of e to the third, and it doesn't really matter what real number you use, but this property says when we multiply by 1, we still get the same real number. Right? -5 times 1 is still -5. Now we'll use these properties in algebra. One use is solving equations, and we'll look at some other examples as well of how we can use these two. Okay, before we get there, let's talk about the inverse property. Another question, once we have this special number, 0 and this special number 1, the two identities, we are interested to know how can we get to those numbers from any other real number. So for instance, if I start at 5, what can I add to 5 to get back to that identity 0? And the answer is -5, and numbers like this that come in pairs that add up to the identity 0 are called inverses. Right? So the inverse property of addition says that when you add two inverses, like 5 and -5, you get the identity 0. Okay? So this is the identity property. Right? An equation like this that shows the identity property. But then the number -5 is the inverse of 5. And it turns out, when we call this the additive inverse, it turns out that the additive inverse of a number is just its opposite. If it's positive, make it negative. If it's negative, make it positive. Okay? So it's the inverse property that tells me that -4 plus 4 is 0, a number and its opposite. And then I can say that -4 and 4 are additive inverses. Additive inverses. Okay, we have an inverse property for multiplication. Same idea. For every real number except for 0, there's another real number, so that when you multiply, you get the identity, the number 1. So one example would be 3 and 1/3. Okay, and 3 times 1/3 is 1. We know that. Now 1/3 is called the multiplicative inverse of 3. So 3 and 1/3 are multiplicative inverses. Now to find the multiplicative inverse, it's not the opposite anymore, it's the reciprocal. So if you had 3 over 1, then you flip it and make it 1 over 3, and the reciprocal is the multiplicative inverse. Okay, if we had the number 6, right, and the question was, what's the additive inverse of 6? Well, the additive inverse is -6, because when I add these I get 0, and the multiplicative inverse of 6 is 1 over 6, because when I multiply those I get 1. Okay, so multiply to get 1, and add inverses to get the additive inverse, or the additive identity, which is 0. Alright, what about 2/3? What's the additive inverse of 2/3? Well, it's the opposite. It's negative 2/3. Okay, and as a check, does 2/3 plus -2/3 equal 0? Yes, it does. Right. Now, when you are asked to find the additive inverse, make sure you don't write this whole equation. The additive inverse is a number, not an equation. So the additive inverse is just this, -2/3. All right, how about the multiplicative inverse of 2/3? Again, you're being asked for a number here as an answer. So they're asking, what number do we multiply by 2/3 to get 1? And the answer is the reciprocal, and you just switch the numerator and denominator to get the reciprocal. Okay, let's do one more example. How about square root 15? What would be its additive inverse? That's going to be negative square root 15. Okay, so just make it negative, the opposite. And its multiplicative inverse, right, well, this is over 1 right now, so it's multiplicative inverse, flip-flop numerator and denominator, and the multiplicative inverse is 1 over square root 15. Here are a couple different ways that we can use the inverse and identity properties. One use is to reduce fractions. So think about how you would reduce 14 over 21. All right, you may notice that both of those have a factor of 7. So the shorthand way of writing this is just to kind of cross these out, divide by 7, and then write what's left as a fraction. All right, so let's write what we're actually doing here. So to use the identity property, we want to fill in the middle steps to justify why this is true. Why does 14 over 21 equal 2/3? Okay, why is its reduced form equal to the original? Well, I can write 14 over 21, and I can rewrite this just emphasizing that 7 is a factor of each. So 14 I can write as 2 times 7, and 21 I can write as 3 times 7. Now there's a rule for multiplying fractions that you can split this up and write this as 2/3 times 7 over 7. Right? And here, 7 over 7, that just equals 1. And it's a different way of writing it. It's in disguise. But really I'm just saying 2/3 times 1 is what? Well, 2/3 times 1 is 2/3. Okay, so that's the identity property there when we said that 2/3 times 7 over 7 is 2/3. Okay, because remember the identity property, it just means a real number A times 1 still equals a real number. Right, and here our real number that we've chosen is 2/3, and then 1 we've just chosen to write it as 7 over 7. Okay, and so what I have here is just a big equation where I started with 14 over 21 and ended up showing that that's the same as 2/3. Okay, another use, rationalizing the denominators of fractions. So looking at the number 4 divided by square root of 2. All right. The denominator is an irrational number, so what it means to rationalize is to rewrite this as an equivalent fraction where the denominator is a rational number, not irrational. All right, so how are we going to do this? This is something that we would have learned in Algebra 2, or maybe Algebra 1. Okay, and what you do is you multiply by whatever the denominator is, multiply by a fraction using that as the numerator and denominator. Right. And the question is, how do I know that that will still give me an equivalent answer? Well, again, this is the identity property because I'm just multiplying it by something that equals 1, so I know that my answer is going to be the same. Okay, and then from there I just multiply 4 square root of 2, and square root of 2 times square root of 2 is square root of 4, which is 2, and then finally I divide. 4 divided by 2 is 2 square root of 2. Okay. Now we covered a couple other concepts dealing with irrational numbers, and you may want to see the textbook example 7 on page 252, and that gives you a couple more examples going through all of those steps. But the important part that I want you to see here is just this step where we multiplied by square root 2 over 2. That's where we used the identity property. Okay, and then a final example of how we can use these properties. Solving equations. 3x equals 5. Okay, now the short way to do this is, you may remember, we divide both sides by 3, cross this out and get x, and then I know that x is 5/3. Now there are a couple steps going on behind the scenes that we just don't usually write. Right, so for instance, why did I choose to divide by 3? Okay, well what I really did, dividing by 3 is the same as multiplying by 1/3. That's what actually happened. And why did I choose 1/3? Well, it's because it's the inverse of 3. I want to get rid of, cancel, undo the 3. All right, and I want to make that a 1. All right, and then 5 times 1/3 is 5/3. Okay, so here I used the inverse property because 1/3 times 3 is the same as 1. So I chose the inverse on purpose. Right. And then finally I know that 1x is the same as x. And that's the identity property. Right. What I'm really doing is I'm replacing 1x with x, and I'm saying that they're the same thing. And that's the identity property, that 1 times a number is just the number itself, even if that number happens to be a variable. Okay, and so I've solved for x, or another way of saying it is that I've found its identity. Okay, the last thing I want to do in this video is a couple examples of identifying which property justifies the changes to some calculations. All right, so maybe pause, see if you can figure out which property of real numbers is illustrated, and then we'll go over the answers. Okay, from your textbook, these are examples 2 and 3. All right, so in example 2, part A, 6 plus 5 equals 5 plus 6. That's the commutative property for addition. We've switched the order of the 5 and the 6. In B, 0 plus 3 is 3. Now this looks like just a normal addition problem, but anytime you see a 0 or 1, be thinking either inverse or identity. So this illustration here is basically showing us that 0 plus 3 is the same thing as 3, so that's the identity property. All right, so if you either see plus 0 or times 1, it's going to be the identity property. In C, what's been done here? Well, we got a 12 and a 36 by multiplying 4 times 3 and 4 times 9, so that's the distributive property. Okay, and then in D, 2/5 times 5/2 equals 1. If you get an answer of 0 or 1, be thinking inverse property. So we've taken a number, 2/5, multiplied by its multiplicative inverse, and we know that that always equals the identity 1. That is the inverse property. And then in E, okay, we have, so look at what's different. The 6, 7, and 3 are all still in the same order, so it's not commutative property. But what's changed is the parentheses. They've moved from around the 6 and 7 to around the 7 and 3. So the grouping has been changed, which makes this the associative property. Okay, and then in example 3, all right, the first one, this one's tempting to say the associative property just because you see 3 numbers and you see a parentheses. But notice that the parentheses actually haven't moved. They're still around the 5 and the 6. So look at what's different. And what's different is actually that the 6 and the 5 have switched places. The order of the numbers has been changed. So this is a trickier example of the commutative property. All right, in B, this one might be tempting to say that this is the identity property because you see a 1 times 7. But the identity property says that 1 times 7 equals 7. That's the identity property. This one is not that. This one, again, is an example of the commutative property. The order of the 1 and the 7 have switched. Okay, and then what do you think about the last one? 5 times 6 plus 2. Right, another tricky example. The parentheses have not moved. It's still around the 6 plus 2, so it's not associative. It's not distributive. We haven't done 5 times 6 and 5 times 2. All right, well, what change has happened? It's that this 6 plus 2 has switched places with the 5. They've flip-flopped, all right, and they've switched order around a multiplication symbol. This is yet another example of the commutative property. Okay, we've switched the 5 and the parentheses, the 6 plus 2. Okay, that's the end of the video. See your textbook if you need some additional examples to help you identify these properties, and go back through and see if you can rework maybe those inverse and identity examples, the reducing fractions, rationalizing denominators, and solving equations. All right, let me know if you have questions, and just be prepared for some questions which apply these properties in new contexts like this. All right, thank you for watching.